You can represent three relationships involving three unknowns with a system of equations. You can represent systems of equations in three variables as graphs in three dimensions. The graph of an equation of the form ax plus by plus cz equals d, where a, b, and c are all non-zero, is a plane. The following slides show the solution of a three-variable system graphically as the intersection of planes. A system of linear equations in three variables can have no solution, one solution, or an infinite number of solutions. First, consider examples with no solution. On the far left, we can see three planes. Each plane intersects both of the other planes, but there are no common points shared between all three planes. To the example in the middle, well, here we have two seemingly parallel planes and a perpendicular plane that intersects both of the original planes, but still we have no points in common, so no solution. And finally, three seemingly parallel planes with no points of intersection, and so no solution. Here's an example with one solution. Note the planes intersect, and there is a single point that's in all three planes. And an example with an infinite number of solutions. Note that all three planes intersect at a line. So all points on that line, the infinitely many points on that line, are solutions of this system. You can use the elimination and substitution methods to solve a system of three equations in three variables by working with the equations in pairs. You will use one of the equations twice. When one point represents the solution of a system of equations in three variables, write it as an ordered triple, x, y, z, in parentheses. Problem 1. Solving a system using elimination. What is the solution of the system? Use elimination. The equations are numbered to make the procedure easier to follow. So note our system. Equation 1, 2x minus y plus z equals 4. Equation 2, x plus 3y minus z equals 11. And equation 3, 4x plus y minus z equals 14. Step 1. Pair the equations to eliminate z. Then you will have two equations in x and y. So notice, equations 1 and 2 have opposite numbers of z's. So if we add equations 1 and 2, we eliminate z and form an equation that now only has the variables x and y. That's labeled here as equation 4, 3x plus 2y equals 15. What we need is a second equation that has only the variables x and y, so we can create a system of equations in two variables and solve it using methods from previous lessons. Notice equations 2 and 3 have the same number of z's, negative z or negative 1z in each case. So if we subtract equation 3 from equation 2, we find negative 3x plus 2y equals negative 3. Step 2, we'll write the new equations we just created as their own system, and then we'll solve for x and y. First, we notice we can add the equations to solve for y by eliminating the x's. Equations 4 plus 5 leads us to 4y equals 12, so y equals 3. And now that we've solved for y and we know y equals 3, we can substitute that into either of our new equations that have only x and y and use that to solve for x. So we choose equation 4, substitute 3 for y, and rewrite it as 3x plus 2 times 3 equals 15, and simplify to find x equals 3. So now we have a value for y, 3, and a value for x, also 3. We can use those to substitute and solve for z. That's step 3. Solve for z. Substitute the values of x and y into one of the original equations. In this case, we've chosen equation 1, 2x minus y plus z equals 4. And substituting, that becomes 2 times 3 minus 3 plus z equals 4, an equation with only z's, so we can solve for z. And doing so, we find that z equals 1. So our final step, step 4, write the solution as an ordered triple. The solution is 3, 3, 1. Your turn. What is the solution of the system? Use elimination.